So let me put down this question. So, how to measure complexity of a hypothesis class. Right. So this is an important question that we need to answer, and the answer to this is what is called as the VC dimension, which is named after two famous scientists who came up with this measure of a hypothesis class, Vapnik and Chervonenkis, two Russian scientists, very popular in machine learning, in some sense the father of statistical learning theory, so to say. They came up with this idea, and before we formally say what this measure of a hypothesis class is, we will talk about an intuitive way to understand what is going on, how to come up with a measure. So, when I say measure, all I am going to do is I am going to associate a number to a hypothesis class. If you give me a hypothesis class, let us say interval hypothesis class, I am going to somehow associate a number to it. If you give me like linear hypothesis class, I am going to associate a number to it, and how exactly this number is associated can be understood using a game, and let me describe that game to you. Again, before I do that description, let's not forget why we are doing this. We are doing this because we want to understand whether train error and test error gets closer and closer to each other as we get more and more samples if we learn from a specific hypothesis class. We know that if the hypothesis class is finite, this happens. We know that if the hypothesis class has the set of all possible classifiers, this does not happen. Now we are asking in between, where we are learning from an infinite hypothesis class, but not necessarily the one with all possible classifiers. There is some structure to it. Now we are asking the question, well, will train error and test error get closer and closer as we get more and more data points? And to answer that, we need to answer the question, how complicated is my hypothesis class? And for that, we need to associate a number to each hypothesis class, and that number is what is called as the VC dimension of a hypothesis class. And how to get this number, I will tell you now. Okay. So, think of this as the following, right. So, fix a hypothesis class. Let us say, so this is a game that let us say you and I are playing, and both of us are fixing a hypothesis class, right. So, linear, interval, whatever it is, right. So, we are both fixing this hypothesis class, and our goal is to figure out what is the complexity of this hypothesis class. How complicated is this hypothesis class? Can I give a number to this hypothesis class in terms of its complexity? That's the question that we are after. So, let us say you are player 1 and I am player 2, right. So, we go in turns. First you start the game, and what you do is that, let us say both of us fix a value n. Let us say it can be n, can even be 1. We can start with n equals 1 and then we can increase n as we go along, but for now let us say we fix a value of n. Your player 1, let us say, picks x1 to xn, right. So, you give me n points, right. So, when I say we have fixed a hypothesis class, it means that we have fixed the input domain and the output domain also. The input domain typically is some RD, output domain is binary classification 0 or 1. So, you know the space from which you are giving me the input, and from that you can choose whatever values you want to, but then you are giving me x1 to xn. This xi typically is in RD, right. So, if our hypotheses are from RD to 0, 1. Okay. So, you do that, and now what I do, I am player 2. Once you give me the points, I will look at these points carefully, and I am going to give you labels for the points that you picked, right. So, I will label these points y1 to yn, yeah. and yi is in 0 1, right. So you give me the data points, you can be smart about choosing your data points, and once you give me, I will be smart about choosing the labels and I will give you the labels. Now once I give you the labels, now your goal is to demonstrate a hypothesis from this bag of hypothesis H, for which for the inputs x1 to xn the labels are y1 to yn, right. So in other words, if player 1 is not able to find a hypothesis small h in the hypothesis bag that we both know about, so what should be the property that I want, such that h of xi equals yi for all I, the game stops, right. So else n equals n plus 1 and game continues. You can even start with n equals 1. So what is happening? We fix n as 1. Now you pick x1 till xn, n points, and show it to me. And once I look at the points, I will label these points. Now your goal is to pick one classifier from the hypothesis class, for which for the points that you gave me, the labels are what I gave you. If you cannot show such a h, then the game has ended. If you can show such a h, then we will set n, we will increase the n and then repeat the game. Your goal as player 1, right. So your goal of player 1 is to play as many rounds as possible. Right. So which means that your goal is to somehow give me x1 to xn such that, you know, for the y1 to yn that I give you, you would somehow find a h which labels them correctly. My goal for player 2, goal of player 2 is to stop the game as early as possible. So this is the game. So now the game can stop, the game may not stop. We will see when the game will stop, when the game will not stop. But this is the game. Now this might seem a little bit abstract. So we'll take one specific example and then we'll both play this game and see where that leads us to, right. So of course I am going to assume what you will do. So because, you know, this is a video, otherwise if it's a class I would have actually asked you to give me some data points, but I cannot do that here. Nevertheless, I hope we'll still have the effect of playing a game. Okay. So let's fix the hypothesis class that we just spoke about, right. So which is our interval, right. So let's fix h as h8, right. So remember, this is just the set of all possible interval classifiers. Within the interval it's 1, outside the interval it's 0. That's the bag that both of us have. Now let's say n equals 1. Now you have to give me one data point. You can give me any data point. Let's say you were smart, you picked this data point, whatever this number is. Let's say this number is 7.3. I don't know, for whatever reason you thought that was the smartest number and you gave me that. Now I have two options. I can either label it as 1 or I can label it as 0. Now I can be smart about my choice, but, you know, does it really matter is the question, because if I label this as +1, now I will give you the label as +1 for the point that you gave me. Now you have to demonstrate one classifier from this bag for which, you know, 7.3 is labeled as +1. If you can, then you have won this round. Of course, you will be able to do that because you can show, you know, let's say you demonstrate this this classifier. Now, is it because I chose a wrong label? Well, I am also trying to stop you as much as possible, But what else could I have done, right? So, the other thing that I could have done is for the 7.3 that you gave me, if I had said 0, then still you would have demonstrated a classifier, a different classifier. Maybe you would have given me this classifier which labels +1 here and 0 everywhere else, and so 7.3 gets a label of 0. So, which means that even in this case you win, right. So, no matter how I label, you have a classifier that will achieve the labeling that I give you, right. So, which means you win this round, right. So, for n equals 1 you have won. So, now the game continues. So, now n equals 2, now n equals 2. So, now you can smartly choose 2 points, sorry, let us say you choose 2 points. Oh, is it too hard? Yeah, let us say this time you chose 3.3 and 7. Well, these are just 2 numbers, it can be anything. Now I have how many options, right? So, I have to label these. I have 4 different options to label these, right? So, I can either label both of them as positive, both of them as negative, one as positive and the other as negative, and vice versa, right? So, let's say I'll try to mentally see if there is a strategy for me to break you. Now, if I give you plus, then what would you do? You would just say, this is the interval, right. So, the interval that encompasses both 3.3 and 7, and that will label both of these as plus and plus. On the other hand, if I give you minus or 0 0, let us call that minus just to indicate the label is 0. If I say minus, then can you come up with a classifier? Well, yes, you can come up with a classifier. Maybe you would just say this is the classifier, right. So, maybe 7.5 and 8 is your interval where it is 1, everywhere else it's 0, and because 3.3 and 7 are both away out of that interval, so they will get minus. Now, what if I say plus minus? Will you be able to give a classifier? Well, you can, right. So, because you can always pick something that surrounds 3.3 but not 7. Symmetrically, so if I say minus plus, you will do this classifier and then you are still okay. So, basically what has happened is, for the 2 points that you picked, no matter how I give the classification, you can still produce a classifier which will realize the labelings that I give, right. So, which means that you have won this round also, right. So, I have lost this round because I do not have a strategy to stop you from giving a classifier, right. So, which realizes my labeling. No matter what I try, you will still be able to win. So, the game continues. So, we will continue this, and now n equals 3. So, if when n equals 3, let us say you give me 3 points now, let us say 1, 3.5 and 7. Now, I have 3 points, I have to give you labels for these 3 points. Now, the question is, I am thinking, do I have a strategy? Now, if I say plus, then you will demonstrate this. If I say minus, you will produce this classifier, right. So, when I say this classifier, it is this classifier basically, right. So, now there are 8 possibilities because there are 3 data points, 2 power 3, 8 possibilities. Now, is there a possibility of labeling for me such that you do not have a realizable classification? Think about this. Pause and think. I'll maybe some of you are already seeing it. I'll tell you the answer now. Now, what I will do is I would do the following. I will label this as plus, this as plus, and this as minus. Now, can you produce a classifier which will label 1 as positive, 7 as positive, whereas 3.5 as 0 or minus, negative? Well, if I have to label 1 and 7 as positive, then both of them should be part of one interval. But whichever interval 1 and 7 are part of, so is 3.5. So, which means 3.5 will also be positive. But I have labeled it as negative. So, there is no classifier in the hypothesis class that we have for which you have a strategy, right. So, to break my labeling, right. So, to realize my labeling. So, I win, and the moment I win, the game stops, right. So, the game stops at n equals 3, yeah. So, this is a case where the game will stop, and we will define the VC dimension, of this interval class as the number of rounds you have a winning strategy. In this case, when n equals 3, I have a winning strategy, but then for n equals 2, you have a winning strategy, which means that the VC dimension is basically 2 in this case. For n equals 2, you have a winning strategy. For n equals 3, well, now again, you can be intelligent about choosing these data points, but remember, no matter how you choose these data points, how intelligently you choose 3 data points, I still have a winning strategy. I will put the middle one. I mean, no matter how you choose 3 data points, there is always going to be a middle one, and I will choose to make the middle ones label as minus and the edges as plus, and you don't have a classifier that labels it that way. And so, it is not like I arbitrarily picked 3.57 here. There is nothing to be intelligent about, right. So, because it is a real line, but then when you have RD, maybe you can be slightly more intelligent, but in this particular case we are talking about real line is as our domain, and for this hypothesis class the VC dimension is 2. So, let me now actually formally state what the VC dimension is. It's precisely what we did here, but then it's good to formally write it down. So, let me do that now, right. So, VC dimension definition. Again, there are multiple formal ways to define this. I am just going to define it at the level that it's sufficient for us. So, the VC dimension of a hypothesis class is D. This is some natural number if two things happens. One, there exists x1 to xd, that is, when I say VC dimension is some value d, which means that as player 1 you should have been able to produce x1 to xd such that for all y1 to yd you can produce a hypothesis from the hypothesis class. There exists a h in h for which h of xi equals yi for all I, right. So, when I say for all y1 to yd, for all possible 2 power d labelings, right. So, no matter which of these 2 power d labelings that I pick, you still have a winning strategy. That is, there exists a h such that h of xi equals yi. That is the first condition. The second condition is that if I have a data set such that the data set size is greater than d, that is, it becomes larger than d, then I have a winning strategy. So, maybe I will put that in blue to say that my strategy is in blue. So, for every data set, no matter how intelligently you pick the data set now, right. So, but then if it has greater than d points, then there exists y1 to yd. I can intelligently choose set of labels for the data points in S such that there does not exist a h which realizes this label. Right. So, the conditionals, see, the conditions are important, the qualifiers are important, right. So, and the first statement is saying that there exists, whenever there exists, somebody is intelligent about it, right. So, there exists x1 to xd, which means that you have intelligently picked x1 to xd such that no matter how I give the labels y1 to yd, you can produce a classifier. There is a classifier h such that h of xi is yi. That is rule number 1, right. So, it should happen for d data points, only then the VC dimension is d, but then it should, for example, here it happened for 1 also, 2 also, right. So, I cannot say VC dimension of n is 1, because for n also, no matter how you give me 1 point, I mean there is a way for you to give me 1 point such that no matter how I label, you will still be able to produce a classifier, but we don't stop there, right. So, that is why the second condition is there, which means that I don't I have a winning strategy for anything above d, right. So, in some sense this is the maximum d for which you have a winning strategy. That is what these two conditions say. So, let us look at the second condition again. It says that for all s, which means that for all data sets which has size greater than d. So, now however intelligent you are, if you produce a data set greater than size d, then I have a winning strategy. That is, which means that there exists some label y1 to ys, which means that by looking at your data set, I can produce a labeling y1 to ys such that no hypothesis in the hypothesis class can label, h of xi equals yi for all I, right. So, which means that I win, for anything greater than d. For anything less than or equal to d, you win. For anything greater than d, I win. And when you find such a d, that d is the VC dimension. Now, note that I mean, of course, directly the this implies that the VC dimension of h int is 2 from whatever analysis that we did. Now, if we worked with the space of all classifiers, right, so then what would have happened? What do you think would be the VC dimension of the space of all classifiers? That is, the hypothesis class, that the bag that we are looking at has all possible classifiers. Now, what do you think would be the VC dimension? Pause and think about it. I will tell you now. Now, if you have all classifiers, then you do not really have to worry so much. You can produce any set of data points. No matter what labels I give you, you will have a classifier which for this data points labels it in the way that I gave you the labels, because the hypothesis class that we are looking at it is so rich that it can map any set of data points to any labels, right. So, which means that the game will never stop. You always have a winning strategy. Player 1 always has a winning strategy. And so, if we look at the space of all possible classifiers, the VC dimension of that hypothesis class is infinity. Now, this kind of captures in a superb way our intuition that by a single number, this is a way to associate a single number to a hypothesis class. And now, for a class where uniform convergence does not hold, the VC dimension is infinity. And for a class where we saw uniform convergence holds, VC dimension is 2 in this specific class, right. Now let's ask, I mean, now we have put this definition, let us look at a couple of more examples to understand what might be the VC dimension of those hypothesis classes, and then we will see why this is a useful thing, right. So, of course, this kind of measures the complexity, that is where we are, but how exactly does it relate to the uniform convergence, we will talk about in a minute, but before that, let us first understand, VC, let us first get used to this idea of VC dimension by looking at a few more examples. Let us do that now.